The first step in this estimation of volumes activity is to work the image in GeoGebra. We have to open the graphics window, and in this window we have to insert the image. We are going to select one of the towers we have available, and this image is going to be displayed in the graphics window. The next part is place this image in the first quadrant. With this, we are going to have only positive numbers. We are going to center the lower left vertex in the origin. Next, we are going to center and zoom the image. After this, we are going to draw the axis of revolution for this tower. The axis of revolution of this tower is going to be a vertical line. So we are going to draw the best vertical line possible. To do this, we are going to use two auxiliary segments, horizontal segments, that are going to have ends at on the edge of the tower. You see, like this. To help us to place this in the best position, we are going to change the style of the points. We are going to select the style in object properties, the cross, for all the four ends for these segments. Like this and this. Okay. Once all four ends are in this new format, we are going to zoom, and we are going to place these ends in the vertex of the edge of the tower. Well, this looks fine. Then we move and amplify. Now this is going to be difficult to place because it's not clear, but we are going to try our best. Well, this possibly a little bit more to the right, like that is pretty much at the end of this line. And then we are going to align the lower segment. We take this point, and we are going to put it more or less at this end, and we are going to place the last end, and sometimes it's difficult to place it, so you have this problem. Just zoom the image a little bit more and place the point in the best position. Now the next part is to draw the midpoints for this segment. Our axis of revolution has to cross these two midpoints, so we have to use the midpoint utility, and we have just to click the ends of the segments, and automatically the midpoints are going to be displayed. Now we are going to draw a line through these two midpoints with this utility, the line utility. Just we have to click the 2 points, and here is our first approach to a vertical line. In the algebra window, you can see the equation for this line. In the slope intercept form, we can see that the slope is 107 negative. This is pretty much vertical, but we are going to try a better vertical line. For this, we have to rotate the image a little bit. To rotate the image, we are going to use the rotation utility. Specifically, we are going to use rotate around a point. We have to click on the image, we have to click on the rotation point, and we are going to rotate 0.54 degrees because it's pretty much corresponding to 107. Now we can see our image in a new position, and our lines are not in the right position. So we have again to zoom out our image and place the ends of our segments in, select the points and place them again in the right position in the corners of the tower. Both segments have to be placed again. We move the point in this corner, this to this corner, and we can see now our slope is negative 1885, much better than before. Now to avoid the image move again, we fix the image. We click and fix object. Now we have to do something else. As you can see, our horizontal segments are not precisely horizontal. This is evidently not horizontal. This is a little bit more. Now, we have to make them horizontal because when they are horizontal, the two revolving lines, the left and the right, have pretty much the same length and the same shape. So the first thing we're going to do is change the rounding to 4 decimal places. And now we're going to see the y coordinates. So to make these segments horizontal, we have to make these two y coordinates equal. So we're going to change this to 10.9. So we change the first one, then the second one. Okay, we have to select the digits and change them. Okay, this is 10.9. And it seems that the top one has not changed, so we select these digits and put 0.9. Now they are equal, and this segment now is horizontal. Now we are going to make this bottom one horizontal also, so we are going to change the y to 5.7. Y coordinate 5.7. Oops, we have some hidden digits over there. We delete them. Now the y coordinate is 5.7, and this is going to be also 5.7. So we just delete the digits, and now the two segments are horizontal. Don't worry, right? Don't worry too much if the points are not necessarily at the original places, like in this case. The measurements are going to be good enough. Okay, now we are ready to draw our revolving line. To do this, we are going to use the polyline function, and we are going to begin at the top point, in this case this point D, and then we are going to draw the points along the edge of the tower. Well, don't worry if at the beginning you don't have your points exactly on the edge. We can correct that later. So the idea is you have enough points to draw the polyline. We are going to close the polyline, so we are going to use two auxiliary points, and we are going to close the polyline. It's extremely important you close the polyline. Okay, we are now ready to align those points that are not exactly on the edge of the tower. So we can just select the point and move it along the line, so we can correct immediately the position of the points. Is very simple. So these points are fine. You correct this one right here, then we move the image a little bit to the top. Here is another point. So this is the time you are really setting the revolving line. So again, we can finish with this last point. Yeah, one more right here. And it's important that you include also the truss structure of the cooling tower, because you are going to compute the entire volume from the top to the floor. Okay, now our cooling tower revolving line is ready, as you can see. We have now to measure the perpendicular distance from the axis of revolution to the revolving line. To measure this distance, we are going to use another segment. This is going to be our ruler, so we have to attach this segment from the axis of revolution to the revolving line. Be careful, because you have to move this segment along the lines. If you hit one of the points in the revolving line, it's going to be impossible to move it. Now we are going to change the style of the ends of this ruler, and also we are going to change the color to distinguish better. We change the color also to the segment. Now you can see that our segment has a different color, as well as the coordinates of the ends and its length. Okay, now this point coordinate, the y coordinate, is going to give me the position of the perpendicular cross-section along the axis of revolution. Now, let's do a trick. We're going to rename this point, usually with a capital C, and with this, we have the two numbers we have to read pretty close. This is going to ease our task. Now, the next is we have to put our ruler perpendicular to the axis of revolution. That is not difficult. You have to have the two y coordinates equal, but you saw that that's a little bit annoying. So this is going to be the trick. Check this out. Draw a perpendicular line to the axis of revolution, pass it through the end of the ruler going through the revolving line. Now, when you align the segment and the perpendicular line, you are going to have the perpendicular distance to the axis of revolution. We are ready now to measure the perpendicular distance to the revolving line. So what we are going to do is begin in the lowest position of the polyline or revolving line. So we are going to displace our ruler and we are going to align the perpendicular line and our segment, our ruler. Sometimes it's difficult, as you can see, so sometimes you have to zoom in, and then, well, the radius of the circular cross-section is there and the y position is over here. Now we have to record, so we are going to use the auxiliary spreadsheet in this GeoGebra software. So we're going to have the vertical position and the radius of the cross-section. So here we're going to record the position, the vertical position of these cross-sections, 538.83, and in this cell the radius of the circular cross-section. Okay, now we move to the next cross-section. So we have to take one end on the polyline and then we align with the perpendicular line again. Okay, there is, and now well, it's taking me a while to align these two lines. Okay, more or less they are over there now. And now 57022 is the vertical position of this cross-section, and the radius of this circular cross-section is 226.79. Okay, now we continue in the way up and we measure the next cross-section, right? So the position is 6.0046 and the radius of this cross-section is 215.19. Yep. Now we are going to repeat this one as many points we have on the polyline. Of course you can measure in a different place, but the points are okay. Now this position is 634.06 and the radius of this cross-section is 2.0405, and you are going to repeat until you reach the top of the line. Okay, once we have all the values, all the cross-sections, positions, and the corresponding radius, we have to compute the scale factor. The scale factor is computed using the height of the tower, the real height in meters of the tower, and the height of the tower but on this screen. Now this is easy to compute, so you subtract the last y position minus the first y position, and in this case is 5.5105, and the real height of this tower is 176 meters. So the scale factor is no more than the quotient of these two numbers, so we divide 176 by 5.5105, and the scale factor is 31.939. So every unit on the screen is the same as 31.9 meters in the real scale. Now we're going to take these numbers and we are going now to work in Microsoft Excel. Why? because it's a more powerful spreadsheet, and well, we are going to use the resources in this spreadsheet. Now we copy and paste, and then we are going to add the index. So the first point is 0.0, then the next one is a 0.1, and then we just drag and drop, and we are going to see that we are going to use a partition of size 19 to approximate the solid of revolution for this tower. Well, when we have all our measurements in Excel, we are going to compute the volume. To compute the volume, we are going to use the ring method, this integral, and we are going to approximate using the trapezoidal rule. So this portion of the formula, yeah, okay. So for this, we have to compute the values at the partition we have defined here. Okay, now it's time to use the scale factor to find the real values of the cooling tower. So we are going to put now the position along the axis of revolution in meters and the radius of the cross sections in meters, and we have just to multiply these numbers times the scale factor. So that's an easy operation. We are going to multiply both columns, so we take the first entry, then times the scale factor, and then we are going to put the dollar symbol in front of the coordinates of the cell where the scale factor is in both columns. And with this, we are going to be free to just drag and drop to compute all the real measurements from the on-screen measurements. Okay, now we have to compute the squares of the radius, so that's simple. Square of the radius is going to be just the square of the elements in this cell. So we just click and square, and then you simply drag, and compute all the squares you need. Well, now in this last column, we are going to put the volumes of the partial cones we have divided the solid, the different portions. So we are going to have here this portion, this formula. So we are going to have pi divided by 2 times the square of the adjacent radius, so this plus this, times the length of the subinterval, so the difference of these two numbers right here. We close the parentheses, and that's the partial volume of this cone. Now we are going to compute all the volumes of all the cones we have, the 19 cones, and then, well, we can see that this is the value for the last two pairs. Now we are going to compute the approximate volume for this cooling tower. So this volume is going to be in cubic meters, and well, is simply the addition of these values in this column. So we have to add these values, and the approximate volume for this cooling tower is 1,559,000 cubic meters.